Howdy, today I'm Flippin Science. We're going to look at the chemical and physical properties of polymers. So science understands we're going to look at organic polymers can have different properties depending on the monomers and degree of cross-linking between chains. So compare physical properties of polymers with different degrees of cross-linking and secondary interactions between polymer chains. Production of synthetic polymers allows the manufacture of materials with a diverse range of properties. So compare the effects of heating on thermoplastic and thermoset polymers. Explain the difference in the ease of recycling of thermoplastic and thermoset polymers. In the next bit we need to talk about bonding between the polymer chains. So you can get primary and secondary bonds occurring between the chains of the polymer, and basically the number of those bonds that you have, that will change the physical properties of the polymer. So if you have a long non-polar chain, so polyethylene that we have here, the only force of attraction between the polyethylene chains is going to be dispersion forces. So the longer the molecules are, the stronger the dispersion forces are, the more rigid your polyethylene will be. So the longer your polymer chain, the stronger the dispersion forces that will occur between the polymer chains, and that will lead to an increase in rigidity and strength. So summarizing that, so if you have polymers that are held together by only dispersion forces, they're not going to be particularly rigid, they're going to be soft and flexible and non-elastic, so that means they won't snap back to the position if you put force on them. They'll normally have low melting and softening points because it doesn't require a lot of energy to break those dispersion forces. So they're very good at being recycled. So your non-polar long chains, they're very good at being recycled easily. You can also get hydrogen bonding between polymer chains if they contain the normal groups that will generate hydrogen bonding. So oxygen, hydrogen, nitrogen, or carbon-oxygen groups can generate hydrogen bonding. So an example is Kevlar. So Kevlar, it's a polyamide. So we've got this amide group that's joining each of the monomers together. Here we have 3 chains. So there's 3 chains of the polymer. Now we can see where we have our nitrogen-hydrogen bond, we can get hydrogen bonding between the hydrogen and the oxygen from the carboxylic acid bit of the dicarboxylic acid monomer. So we can get hydrogen bonding between those atoms, and that will occur all the way throughout the molecules. So all the way along the molecule chains. So all the way along the polymer chains you'll get that hydrogen bonding occurring. And this will make the polymer stronger, so it'll resist force better. It'll be more rigid, so it'll be more solid, but it also will be elastic because you can break those hydrogen bonds where you put force on the polymer, but then those hydrogen bonds will reform as soon as the molecules get close to each other again. So those are examples of secondary bonding. An example of a primary bond, you can get covalent bonds between the polymer chains, and we refer to those as cross-links. So if we look at styrene here, we've made the polystyrene molecule, but we're also encouraging some cross-links between one polymer chain of the polystyrene and a second polymer chain of the polystyrene. So by having that covalent bond in there, that's going to change the physical properties of the polymer again. It's going to make it a lot more stronger, a lot more rigid, and a lot more hard, a lot more elastic, and also make it more durable and therefore more difficult to recycle as well. So by looking at those types of bonding between the chains in a polymer, we can break up our polymers into 2 big groups, the thermoplastics and the thermosets. We'll start with the thermoplastics. So when you have a thermoplastic, if you heat it up, the plastic will soften. You can deform it into another shape, and then you can cool it down again, and then you can heat it up and melt it and reshape it and cool it down again, and so on and so on and so on. So you can do that repeatedly. So they are plastic when they're heated up, so that's where the thermo and plastic come from. Because you can reshape these readily and melt them and mix them together, they're very easy to recycle. So some examples that we have, polyethylene terephthalate, which is your Coke bottles, polypropylene, a few other plastics like that. Thermoplastics are different. When they form, you get your strong bonding occurring between the polymer chains, and that's usually in the form of cross-links. And what that does is it sets the shape of the polymer. So what that means is once it's formed, it's very hard to break those bonds between the polymer chains. And when it comes to recycling, that makes it much more difficult. When you heat up a thermoset polymer, rather than melting, what will happen is it will start to burn. And if it burns, then you can't really use it. So 3, 2, 1. So some examples of thermosets are rubber. So rubber, once it forms, you get those cross links between the chains of the latex. It's very hard to break them, so it's very difficult to recycle. Epoxy resins, these are used as glues. They're good at sticking things together. Once they form though, they're stuck. It's very hard to remove them from a surface. So here's an example question. It says polypropylene softens when heated. Stated term used to describe a polymer that has that property. Well, that's going to be a thermoplastic. Then it says state one advantage of that property. Thermoplastics are readily recyclable. The last question here, we've got a table. It shows us the structural formula of several polymers. It's also got our melting point range for several polymers. The question says, explain with reference to the information in the table and to secondary interactions between the polymer chains why stanol is a preferred polymer for the use in the engines of motor vehicles. If we look at stanol, the first thing I'm going to say is it's got the highest melting range out of any of the polymers, which makes it suitable for use in conditions where there's high temperatures, for example in the engine bay. Why? If we look at nylon 6, we can see that we have one polar group here, so we've got an NH, and we've also got another polar group over here, so a C double bond O. So when we get the polymers, when we get the polymer being produced, we can get hydrogen bonding occurring between those chains. So that's going to give it a higher melting point. If we look at polypropylene, when we look at how it will join together, it's all non-polar over here. So the only force of attraction between the polymer chains is going to be dispersion forces. So the dispersion forces between the chains will require less energy for the polymer to melt. It doesn't require as much energy to separate the dispersion forces, so therefore it's got a lower melting point range. If we look at nylon 6, we can see that it's got hydrogen bonding between the chains at one point per monomer. So this one will attract to another polymer chain at that point. So there's one point that hydrogen bonding will occur between the monomers. If we have a look now at stanol though, we can see we've got a polar group here, a polar group here, a polar group here, and a polar group here. So what that means is that we have 4 points per monomer where we can get hydrogen bonding occurring between the chains. And what that will lead to is a higher melting point because we're getting stronger secondary interactions between the polymer chains which require a lot more energy to separate. So to summarize, polypropylene is only going to have dispersion forces occurring between the polymer chains. And that's not going to require as much energy to separate the chains and therefore to melt the polymer. Nylon 6, it has 2 points where we can get hydrogen bonding occurring per monomer. So this point here and this point here. So between the chains you'll have 2 points of hydrogen bonding. Hydrogen bonding will require a lot more energy to separate the polymer chains than just dispersion forces in polypropylene. But then if we look at stanol, it has a lot more opportunity for hydrogen bonding to occur between the polymer chains per monomer, or per monomer in the polymer chains. So because there's twice as many opportunities for hydrogen bonding per monomer, that's going to increase the melting point again as well. So that's it for Flipping Science today. See ya.